Welcome back. We are now officially on to day 3 of Enzymes. So believe it or not, this is actually your last day of notes before your test on Friday. So the rest of this week, we will be working on some labs for this unit, as well as a test review. So your test will be on Friday of this week. Your test is going to cover cells, biomolecules, and enzymes. So make sure that you are caught up on all of those notes and are ready to go for that test on Friday. But today we're going to be finishing up enzymes. And our aim for today is how does pH affect enzyme activity? So some things that we should jot down. By now, you should know some things about enzymes. You should know that they are catalysts, which means they speed up reactions. They speed up the rate of reactions. Okay, and you should know that they are proteins, which means that they are made up of amino acids. So anytime I write RXN, that means reaction. I'm just too lazy to write the whole word. Okay, so how does pH affect enzyme activity? Well, what is pH? Today we're going to find out. So we're going to leave that blank right now. And at the end of today's lesson, you should be able to fill in some information on what exactly is pH. All right, so now I want you guys to answer the do now question. You've got 3 questions and 2 graphs. Use those graphs to answer the questions. Pause this video and press play when you're ready to go over it. So number 1 said, what is the ideal temperature for the enzyme in graph A? So remember when we say ideal, we're talking about the best. What is the best temperature for enzyme activity in graph A? So graph A is talking about temperature and enzyme activity. And we see in this graph that as temperature increases up to a certain point, enzyme activity increases as well. So we see that enzyme activity is increasing. And it increases up into a range of around 35 to 40 degrees Celsius. And you guys might notice that this is actually the same temperature that I mentioned in day 2. So enzymes work best generally at a temperature of 35 to 40 degrees Celsius. And we see that after 40 degrees Celsius is reached, that enzyme activity is actually going to decrease again. So it works best at a range of 35 to 40 degrees Celsius, but anywhere outside of that temperature, it's not going to work as well. All right, number 2, what is the ideal pH for the enzyme in graph B? So I remember again, ideal means best. And this time we're looking at graph B. So pH versus enzyme activity, we see that as pH increases to a certain point, enzyme activity increases as well. And that best pH is actually going to be at a pH of 7. Okay, so the pH of 7. And once again, after we pass that pH of 7, it's going to decrease again. So whenever you're talking about the ideal or the optimum temperature of pH, you're always going to look for the highest point in the graph. So I'll do that in red. You'll notice that both of these ideals are the highest point on the graph. Okay. Number 3, imagine that the enzyme in graph B is placed in a new environment with a pH value of 3. Using graph B, describe how this enzyme will function. So for this one, we're going to be using graph B, where we're still looking at pH, and we're going to look at a pH of 3. So that would be around here if we use this bottom scale. And using that, we can map the rate of enzyme activity by following that over with a straight line. And looking at that rate of enzyme activity, if we know that this is 0 and this is, let's say 100, it's actually super, super low. So that rate of enzyme activity is going to not work well at all. It's going to be super, super slow. Okay, so this enzyme at a pH of 3, this enzyme will function very slowly. Okay, enzyme B works best at a pH of 7, and it will not work as well at a pH of 3. So we see that at a pH of 3, that enzyme activity is going to be very, very slow. The rate of activity is going to be not fast at all, okay? We see that it works best at a pH of 7, which most enzymes do, but anywhere outside of that range, it's not going to work as well. All right, so let's move on. Today, we're going to start off with an independent reading. So I will read this passage with you, and as I do that, I want you to stop and jot and answer the questions at the bottom. So the passage is an intro to pH. Even though you've never set foot in a chemistry lab, chances are you know a thing or two about acids and bases. For instance, have you ever drank orange juice or soda? If so, you know some common acidic solutions. And if you've ever used baking soda or egg whites while cooking, then you're familiar with some bases as well. You may have noticed that acidic things tend to taste sour, or that some basic things like soap tend to be slippery. But what does it actually mean for something to be acidic or basic? To give you the short answer, an acidic solution has a high concentration of hydrogen ions, greater than that of pure water. And a basic solution has a low low hydrogen concentration, less than that of pure water. So using that information, I want you to independently identify 2 additional acidic and basic solutions that you encounter every day. So we've already seen that some examples of acidic solutions are things like orange juice or soda, and some examples of basic solutions are going to be things like baking soda or egg whites. So use that information to write down 2 additional acids and bases that you encounter every day. Pause this video, then we'll go over it together. All right, so some additional acidic solutions are going to be things like vinegar or coffee. Okay, those are 2 acidic solutions, which means they have a high concentration of hydrogen ions. And we abbreviate hydrogen ions by just saying H+. All right, and 2 basic solutions. So we've already said soap, but you could have said something like laundry detergent or toothpaste. Okay, so basic solutions have a low concentration of hydrogen ions. Okay, and if you have a question about an acidic or basic solution that you have written down, send me a message on Remind and I can let you know if you were correct. Okay, so now this says partner work, but you're gonna do it with yourself. So the pH scale is used to rank solutions in terms of acidity or basicity, and it ranges from 0 to 14. Anything below 7 is acidic, and anything above 7 is basic or alkaline. Okay, so you can see on this scale, this is our pH scale. As you just read, it ranges from 0 to 14. So things that range from 0 to 6 or 0 to 7 really is going to be acidic. And anything that ranges from 8 to 14 is going to be basic or alkaline. And 7 is going to be our magic number right here. 7 means a neutral pH, so it's neither acidic nor basic, it's perfectly neutral. And something that has a pH of 7, that neutral pH, is going to be water. So water is basically our middle ground for whether things are going to be acidic or basic. So now, using that information, I want you to take these vocabulary words that are in the box and place them where you think that they would go on this pH scale. So if you think that they are basic or alkaline, they're going to be somewhere between 8 and 14 up here. And if you think that they are acidic, they're going to be somewhere between 6 and 0 down here. So you're trying to place urine, bleach, black coffee, seawater, and gastric acid. Now, gastric acid is going to be stomach acid. All right, so go ahead and pause this video, place those things on your pH scale, and then press play when you're ready to go over it. All right, so one more time, we are dealing with a pH scale here. That pH scale is going to range from 0 to 14. Anything that from 14 to 8 is going to be, actually, I think I did that in blue on the last one, yeah. Anything from 8 to 14 is going to be basic or alkaline. And anything that ranges from 6 to 0 is going to be acidic. Which means that 7 is our middle ground, okay? This is neutral territory. So a neutral pH is a pH of 7, and that's water. Water is perfectly neutral. All right, so first up, you should have placed bleach as number 13. So bleach has a pH of 13, meaning it is very, very basic. So very alkaline, very basic. That's going to be like a soapy texture, right? So bleach is basic. Next up, seawater is going to have a pH of 8. So remember we said that water is neutral, but seawater, because it has some salt in it, has a slightly higher pH. So it is still relatively basic or alkaline, but it is closer to neutral ground. Number 6 is, her pH of 6 is urine. So urine is mainly composed of water. So that's why it's close to 7. But because of the different ions and things that it contains, it's actually going to be a little bit more acidic. So that's why we place it at a pH of 6, because of that acidic content. But it's not very acidic, which is why it's closer to 7. Black coffee is going to have a pH of 5. So once again, it is pretty acidic. That's why if you drink too much coffee, the enamel of your teeth actually wears down, because that very, very acidic is going to be gastric acid. And remember, gastric acid is talking about your stomach acid. And this makes sense, right? We have to have something super acidic in our stomach to break down the food that we're eating and corrode away that food. So we're actually going to describe gastric acid as super corrosive, which means it wears holes in things. It really breaks things down. So it breaks down substances. Right. And fun fact about gastric acid, you may have heard of people getting stomach ulcers, right? And that's when their gastric acid actually wears holes in the side of their stomach, because that pH is really just so acidic. So it's so acidic, it actually burns holes into their skin. Ooh. All right. Now, 2 more important things to note is that the cytoplasm of your cells has a pH of 6.8, which is super close to 7, remember? And that's because, remember, we've learned that cytoplasm is mostly contained of water. So it makes sense that it has a pH of almost 7, because it's composed of so much water. Same thing with your blood. Your blood has a pH of 7.4. Once again, it's almost exactly neutral, because that has so much water in it. So whenever you think of water, I want you to think a pH of 7. That is a neutral pH. 8 to 14 is basic, where alkaline is another word we use. And anything from 6 to 0 is going to be acidic. All right, next up, we've got a few more things to note about enzymes. So enzymes work best within specific temperature and pH ranges, and suboptimal conditions can cause an enzyme to lose its ability to bind to a substrate. Each enzyme has an optimum pH range. Changing this pH range outside of this range, changing the pH outside of this range will slow enzyme activity. Extreme pH values can cause enzymes to denature. So before we move on further, I do want you to recall, what is a substrate? So, okay, so pause this video, answer what is a substrate, and then press play. So if you remember from one of our last videos, the substrate is going to be the piece that connects. I'm going to do this in a different color, actually. The substrate is the molecule that attaches to our enzyme. So the substrate is the molecule that attaches to the enzyme. And remember that they have to have the same shape. Okay, so they have to fit together like puzzle pieces in order for that reaction to occur. Now, what does denature mean? So I want you to brainstorm before I actually give you the answer. And I want you to brainstorm by looking at this picture. So this is what happens when an enzyme denatures. So look at how the enzyme is normally and look at what happens when it's denatured. And think about, what do you think that means? So based on what you just read, based on what this picture shows you, what does the word denature mean? Okay, so the word denature is an alteration of the natural qualities of that enzyme. So a change in the environment may cause permanent change in the shape of the enzyme or the active site. And because we've got a change in that active site, this will cause the enzyme to not work. So denaturing means that you're going to change the shape of that enzyme. It almost looks like the enzyme is melting because that enzyme is changing shape. Once it gets outside of its certain pH or temperature range, that enzyme is going to stop functioning. Because it almost looks like that enzyme is melting, the substrate isn't going to be able to fit in that active site anymore. So if this substrate comes along, so it's the same substrate we used before, it can no longer fit in that active site. And remember, the active site is going to be, let's do it yellow. This is going to be our active site, right? Where that enzyme bonds. But because we see that the active site shape is changing, when it's denatured, that means that the substrate can no longer fit. It can't fit into that pocket anymore. And if the substrate can't fit in the pocket, that means that the chemical reaction can't occur. So change in active site equals no chemical reaction. All right, so once again, this causes the enzyme to not work. So anytime we go in a pH range or temperature range outside of that optimum condition, that enzyme is going to denature, which means the chemical reaction can't occur because the puzzle pieces don't fit. So now, this is not part of your assignment. All right, so now on your worksheet, there is a link to an Amoeba Sisters video. I would recommend that you watch this if you have not already. It talks about enzymes and everything you guys need to know. Other than that, all that I need you to do is complete your exit ticket, press submit on your notes, and have a wonderful day. Let me know if you have any questions. I'm here to help you guys out. I'll see you tomorrow.